to send me an email. And this is my email address, so you can check whether I gave you the correct email. And typically, I'm trying to reply to all the email if I'm able to. But anyway, I will try to do all my best. So this is, now things start to get more and more complicated. I'm sorry, I have to go through, okay? Anyway, so I would like to start with something that looks strange. Now you need to be a little bit attentive. So here I have three beams actually. So a yellow beam and a red beam. And then the yellow beam is reflected by this mirror, okay, you see. So the yellow beam is going down, down, down here, and then is imaged on this camera, okay? And now this is the result of the image that we are doing on the camera, poor guys. Then we have the red beam, and you see the red beam is going here, is going there, is reflected by this mirror here, and is coming back, and then is stopped, okay? The yellow and the red beam are made by entangled photons. And now we perform an experiment. No, dov'è qua? Okay, so we are doing an experiment. You see what is happening here? Okay, so what you see is the fact that now we are blocking the red beam. But the red beam is the one that is moving there, is blocked. Okay? And so we are blocking the red beam, and we are looking at the yellow beam. And what happens? The image of the yellow beam is modified. So we do the experiment. Now you try to understand. So we are blocking the red beam, and we are looking at the yellow beam, but the image of the yellow beam is changed. You see? What is happening? So we are affecting the red photons, and we are looking at the yellow photon. But the yellow photon change their properties if we are changing the red photon. Okay? So this is something that quantum mechanics can allow you. And this technique is called undetected photon imaging. And is a quite strange phenomena by which we are observing an object without looking at. That's strange, isn't it? So you see here the red photon. So this is an experiment. So the red photon are those photons that are interacting with the object. But we are not looking at the red photons. We are looking at the yellow photon. And what do we see is the fact that the properties of the yellow photon are changed because what we are changing is the properties of the red photon. And so we are looking at an object by using photons that have not interacted with that object. So this is completely off from any classical explanation. Okay? So the whole explanation is coming from quantum mechanics. And the explanation coming from quantum mechanics, I will be more specific in a while, is associated to the fact that now what we are dealing with are entangled photons. So this is an evidence of the properties of entangled photons that you can see on a macroscopic object. Okay? You can imagine the kind of application of this kind of properties. If I'm using entangled light, I can observe, being in this room, something that is happening on the nearby room. Okay? Because I'm not using the light that is interacting with that photon. And so this is one of the experiment that Anton Zellinger was proposing and was demonstrating. So Anton Zellinger, Nobel Prize winner. So you see why he has got the Nobel Prize. And the experiment here is an experiment that is done in the lab. And the one who is doing the experiment is not me, clearly, but is Chiara Michelini, that is one PhD student in my group. And what she's trying to do is that she's trying to develop a system that enables doing a quantum mechanics experiment on a table, okay, for a kind of application that is related on quantum measurements, okay? So this small movie was just to try to motivate you on the effort to understand what is happening on the quantum scale, okay? This is completely different from what we are used at. And it can happen on a macroscopic scale, and you were witnessing the effect. So let me talk about single photons. And now things are starting to get complicated, okay? And I try to be as simple as I can. But now things are starting complicated. So what is a single photon? So a single photon is a true single photon, okay? And the fact that is a true single photon is manifested by a property that is called anti-bunching properties of the photon. You see that we start to do things that are difficult. But things are getting more and more difficult. So what is the properties of bunching or anti-bunching? So let us assume to have 3 different kinds of photons. So in one case, we have anti-bunched photon. In the other case, we have random photons. And in the third case, we have bunched photons. So here we use light just to represent that instead of having a single photon, so we have a few of those photons that as a function of time are propagating. Okay? You see that we are exploiting the granularity properties of the matter. And then we do an experiment. Okay? We do an experiment with a random a sequence of photon or with a bunched sequence of photon. And so this experiment is a simple beam splitter experiment. So what we do is that we take our beam of photon, of light, and then we make this beam of light to interact with the beam splitter. So the result of the interaction is the fact that the light can be partially transmitted or partially reflected. So this beam splitter is a 50% beam splitter. So we have the light that is coming on top of the beam splitter. So this beam splitter is transmitting 50% of the light and is reflecting 50% of the light. So this is the transmitted light and here is the reflected light. Okay. So this is very simple. So in any optical lab you have many of those. Okay? Because you need to use those a system just to divide a beam. And this is the reason why it's called a beam splitter. Now we perform an experiment with a sequence, a temporal sequence of photons. Okay, now we have some photons that as a function of time do propagate. So when a photon arrives in this point, you have that the photon can go either in this way or can go in that way. Okay? If now we have a detector here, if the photon is going here, the detector click. If the photon is going there, the detector click. What does it mean, click? Means that it measures the photon. Okay? So you have a click here and a click there. And now what you do, you try to do a correlation between the two detectors. What does it mean, a correlation? It means that you have a signal that is high if both photons click, and so you say the correlation is 1 because we had a click here and we had a click there. Okay? Or you get 0 correlation, so no, I'm getting confused. Wait. So, wrong. So we get a 1 if both clicked. Yes, no, this is correct. We get 1 if both clicked, or we get 0 if one or the other clicked. Okay? It's clear? So this is the correlation. So we have one strong correlation if both are clicking, or we get only a 0 correlation if one or the other clicked. Okay? And then we performed the experiment with the different quality of the light. So a random light is the light that is emitted by a black body. Okay? So few photons that are sequentially randomly. And therefore, so in an observation time window, you may end up to have 2 photons. So if you have 2 photons, it means that the probability that one photon is transmitted and one photon is reflected is high. And therefore, you may end up with a situation where both detector click, and so you have a strong correlation. Okay? So you have the temporal response of your photodetector, okay? A certain time window where the photodetector is measuring the photons. So then you consider a bunched light that is the typical light that is coming out from a coherent sources. And so also in this case, so the probability to have both photons that arrive and both photodetector clicks is high. But now let us assuming the fact that you have a single photon. So now, if you have a single photon, what happens is that the photons, because you have only one photon, so the photon can go there or here. And so this detector can click, or the other detector can click. And therefore, the correlation between the click of the 2 detectors is equal to 0. Okay? And so this is a property that is characteristic of single photons. The property is that if you now look at the click of this detector as a function of the time difference between the click of that other detector, you have that the clicks will be high. The correlation will be high. A large number of event where both detector clicks. But then, when the time difference between the click of the 2 detector is equal to 0, meaning the chance to have that both detectors are clicking at the same time, so this correlation should go to 0. Okay? And this is a characteristic properties of a single photon. And it's called anti-bunching, meaning that the single photons are well isolated with respect to the other photons. Okay? In a thermal emitter, so you may end up with 2 photons that are emitted at the same time. In a coherent laser, you have a Poissonian distribution of the emission. So many photons with many events with a single photon, many events with 2 photons, and so on and so forth. And so therefore, if you do this kind of experiment with a laser, so you do not get this 0. Okay? And so the quality of the 0, so the amount of 0 that you measure, is a properties of the a single photon source that you are generating. And so this is a strong characteristic of single photons. They are appearing in a sequence of very well separated events. It's called anti-bunched light. And so this is a property of the light. Then, a single photon is a photon that is a true single photon state, a true state. So this single photon has no correlation with other photons. So you describe this fact by saying that this single photon is characterized by its own wave function, which is independent from the characteristic and the wave function of the other photons. For example, an entangled photon state is not a single photon, because the two photons are strongly correlated between them. Okay? So a single photon is a photon that is independent. If you have two photons, the overall wave function, so let's use capital letters. The overall wave function of two photons, if those two photons are single photons, the overall wave function will be the product between the wave function of the first photon times the wave function of the second photon. Okay? Instead, if the two photons are correlated, the wave function is the sum of the wave function of the photons in a state plus the wave function of the photon in another state. So you have a strong correlation between the two photons, so that the measurements of one photon determine the state of the other photon. If the two photons are single photons, the measurements of one photon does not determine the state of the second photon. No quantum correlation. So once we have defined what a single photon is, a pure state is a true single photon, so then we can say, how should be the characteristic of the source of those single photons? The first desired characteristic is the fact that we want to have the photons when we need to have those photons. And so the characteristic of the source, the ideal single photon source, should be deterministic. We press a button and then the photon is emitted. We know when the photon is emitted. The second characteristic is associated to the concept of that the photons that are generated by this photon source should be indistinguishable. I should not be able to distinguish the first photon emitted by the source and the second photon emitted by the source. And the reason why we want to have these properties is because then we want to be able to do interference, quantum interference measurements. How can we measure whether the two photons are indistinguishable or not? So the kind of experiment that we can do is called Ungo-Mandel measurements or Ungo-Mandel effect, because this is a quite standard experiment which is based only on the properties of a beam splitter, on the use of a beam splitter, that allow us to determine whether the two photons can be distinguished or not. So let us try to perform this experiment. So in this experiment, what we have a beam splitter. We already know what a beam splitter is. It's simply a piece of glass tilted at an angle with respect to the beam. And so here we have, it's called a cube beam splitter, but it's nothing else than a beam splitter. So we have a beam splitter, and then in this beam splitter, if the light is reflected, so it is reflected with a certain reflection coefficient, IR. If the light is transmitted, it is transmitted with a certain transmission coefficient T. Okay? So those are the properties of our beam splitter. And now what we do is that we measure the probability with so the correlation, so the second order coherence function is called. So we measure the correlation between the measurements from two detectors. And we wonder whether we have clicked here or clicked there. Okay? So with the single photon, we already know the reply, the response, the answer. With two photons, the situation is getting more and more interesting. So let us assume to have two photons. Now, one photon is coming here, the first photon. The second photon is coming there, the second photon. Now I'm considering one of those two photons, so for example, this one. So this photon can be reflected, or this photon can be transmitted. Then I do consider that other one. So this photon can be transmitted, or it can be reflected. And now I have the situation of, since the two photons are sent at the same time on the beam splitter, I could have the situation where I have the two photons here. I can have the situation to have the two photons there. I can have the situation of having one photon here and one photon there, or I can have the situation of having one photon here or one photon there. Now, I do assume that the two photons are indistinguishable, meaning that I cannot distinguish, I have no means to distinguish which one is what. Okay? Meaning that I cannot distinguish whether this arrow blue is coming from this photon here or is coming from that photon there, because the two photons are exactly the same. I cannot say this is Bob, this is Alice. They are exactly the same. I cannot say that the photon that I'm measuring here is coming from 2 or is coming from 1. The same there. And therefore, now I have to compute the probability that my detectors click. Meaning that the probability to have two photons here, to have two photons there, to have one photon here, and to have one photon there. However, this situation here is quite complicated situation. Why is complicated? It's complicated because if the two photons are indistinguishable, I cannot say that I cannot distinguish between a situation where the two photons were both reflected by the beam splitter, or the two photons were both transmitted by the beam splitter. So, from the point of view of my measurements, this situation and that situation is exactly the same. I cannot distinguish among those situations. And therefore, when I'm computing the probability, I have to sum the square of the probability that the photon realized this situation or the probability that the photon realized that situation. But what is different in those two situations is the fact that in the reflection coefficient that is describing what is happening at the beam splitter, I have the imaginary number I. And when I do square, because the probability is the square, and when I do square I get -1. And therefore it happens that the probability of having both photons transmitted and the probability of having both photons reflected, since the presence of this -1, the two probability add up to 0. Okay? And therefore, what does it mean? It means that now, if I do measure the probability, if I do measure the correlation between this detector and the click of this detector and the click of that detector, I have the fact that by measuring the delay between the arrival time of this and that, I have that the situation that where both detector click contemporaneously is equal to 0. And is equal to 0 because I could never have the situation where both photons are reflected or both photons are transmitted. Okay? And this is a characteristic of the fact that the two photons are indistinguishable. Okay? So, if the delay between the two photons is larger than 1, then the probability that this click and that other click at the same time is equal to 1. If the delay between the two photons is equal to 0, I cannot distinguish between the two photons, and therefore this probability here is going to 0. And so, the probability to get at the same time both detector clicking is going to 0. So this Unge-Mandel effect is a measure of the degree of the indistinguishability of the photons. And these properties of having photons that are indistinguishable is essentially for any quantum application of my photons. Okay? In quantum computing experiment, I do not want that the result of the calculation depends on the specific photon that I'm using. Okay? Any photon should give me the proper result of my calculation. And so those are the properties that I'm looking when I'm developing a single photon source. So I'm looking that the photons should be in a pure state, so true single. I would like to have a deterministic source, and I would like to have photons that are indistinguishable. In order to measure the degree of pure state that I have, the measurements, so the parameter that I'm using is called the purity. Okay? So the purity is a measure on how good is my single photon state with respect to the ideal pure single photon state. Okay? I will come back on the concept of the purity. So, the first way to generate a single photons is to simply get a laser and then attenuate the laser. Okay? So this is a simple way. I reduce the number of photons that are coming from the laser up to a level where I have only few photons that are propagating. And so this is as the green are the advantages, the red are the disadvantages. So the big advantage is the fact that this is a super easy implementation. Okay? So you can do in any lab. Okay? In any experiment, so you take a laser, this laser pointer here, you take the laser pointer, you attenuate at the level where you are able to distinguish all the single photons that are coming. What are the problems? The problems are associated to the fact that the source is not deterministic. Since I am attenuating, I don't know whether the photon is coming or not. The second problem is associated to the statistical properties of the distribution of the photon states. Okay? So this is the statistical distribution of the photons based on the number of photons that I have in this photon state. Okay, when I have 0, it means that in the photon state I do not have photons. So it's the vacuum state. Okay? And in this kind of source, most of the time, I don't measure photons. And therefore, the probability, so the distribution of 0 photon state is large. Clearly, this is something that I do not want, because if I do not have photons, I cannot manipulate the photons. And then, having one photon is given by a certain statistic, having 2 photons is smaller probability, and so going down. So this kind of statistics is called a Poissonian statistics, and is the statistic that describes the source of photons coming from a laser. It is characterized by the fact that the average number of photons is equal to the standard deviation of the photon number. Okay? So this is not good. We do use this kind of source because it's very simple to implement, but has this caveat, this problem. So then there is another possibility. We use an atomic system. Okay, so what we do is that we have a 2-level system, like in a quantum dot, like in an atom, like in a defect center. So there are many implementations of this 2-level system. And then in this case, so we simply excite the electrons on the high energy level, and so the relaxation of the electrons generated one photon. And so in this case, so the system has very good properties in terms of deterministic emission. So we know when the photon is coming out because we pump, we excite the electron, and therefore after the excitation we have the recombination, we get one photon. Very good. Since only one electron recombine, we have only one photon emitted. And so this is a really truly single photon state. So if we look at the statistic of the emission, so we have that the probability of getting one photon in the photon state is extremely high. We only have one photon. The probability to have more photons is negligible. Why is negligible? Because we have only one electron that transits here. So the transition is only from one electron. Okay? So the ideal situation is where we are considering, for example, an isolated quantum dots, or we are considering an isolated defects. Okay? Therefore, so what we are doing is that we are trying to isolate the single quantum dots, we are trying to isolate the single defects in order to get a single photon emitted. But the point you are raising is one of the most difficult aspects of this kind of sources, meaning that they are, on one side, difficult to implement on a chip, on a circuit, because it's quite difficult to put a single atom on top of a photonic integrated circuit. It's quite difficult to put defects on the single photon sources. And then the most problematic aspects are associated with the low fabrication reproducibility, because the point you were raising, and most difficult is the fact that if we have more than one photon source, those photon sources can be distinguished. Let us assume to have two defect centers that are emitting two photons. So we have two photon sources. They do emit two photons. But then one defect is interacting in a way with the lattice, the other is interacting in another way with the lattice, and therefore the properties of the emitted photon are different by, let's say, a few nano electron volt. Okay? So the lattice configuration around the defect is different, so the transition energy is slightly different, and therefore I can distinguish the photon. Okay? So there are systems that are based, I will show you in a while, systems that are based on this kind of sources, and the main difficulty is to get indistinguishable photon sources, because they do depend too much on how the actual implementation of the source is realized. The good property is that they are bright, so they are able to emit a huge flux of single photons. A big difficulty is the fact that since they are not integrated in the circuit, so you have losses associated to the insertion of those single photons in the circuit. However, people are developing Xanadu, the example of quantum computer I've been told you before. So those quantum computers are based on this kind of sources. Then there is another technology. And this technology is based on what is called heralded single photon sources. Okay, so the idea of the heralded single photon sources is the following. So let us start from an entangled photon pairs. So let us start from a photon pairs that is correlated in time. Correlated in time means that in a certain time instant, I know that I have the two photons because they are correlated in time. So they do happen to be on the same time interval. So they are strongly correlated in time. Okay? It does not happen that one comes before the other. So they are coming at the same instant. So then I have a detector, and then I have a quantum circuit. Then what I'm doing is the following. Let me see if it is really. Yes. So then what I'm doing is that I'm using one of the two detectors to measure the presence of the other photon. And so what it means that now the measurements of this photon that is coming from the correlated photon pair is heralding to the other detector that inside the circuit is coming one photon. Okay? So here the concept is that I use the measurements of one of the two photons in the pair to trigger the presence, to announce the presence of my single photon in the quantum circuit, and therefore to perform the measurements. Okay? So this is the concept. So this is a single photon source. I have a single photon that is heralded by the measurements of the correlated photon in the pair. Okay? And therefore, in order to make these correlated these heralded photon sources, what I do need is to have an entangled photon pair. So I do start by an entangled photon pair, I do measure one photon in the pair, and then I use the other photon as the single photon that has been heralded by the measurements of the first one. What are the advantages? As I will show you, so those are very easy to be implemented in a chip. So they have a good single photon behavior, meaning that if I do the measurements, so the state is a very anti-bunched state. So how do we do the anti-bunching measurements in this case? In this case, remember, we have two photons. And therefore, now we need to have three detectors. Why three detectors? Because two detectors need to be used in order to make an Ungo-Mandel measurements. And the other detector is to trigger the Ungo-Mandel measurements. I need to announce to the Ungo-Mandel experiment that my single photon arrived. And therefore, I need to have three detectors. So one detector that is heralding the presence of the photons. And so this is the detector that measures the heralder photon. And then I have the two detectors that perform the Ungo-Mandel experiment only in the presence of my heralder photon. And therefore, I look at the correlation of those two detectors as a function of the triggering provided by this heralder photon. And so this quantity is called the heralded second order correlation function or coherence function. Okay? And so this is quite mathematically, but this is the formula that defines my heralding, my anti-bunching statistics. And if I do the experiment of this quantity, when I'm performing the heralding, I see that for a time delay between the two detectors in the single photon measurements, I see that the Ungo-Mandel measurements give me a 0. Okay? So this means that indeed this single photon that has been heralded by the measurements of the other photon is in a truly pure quantum state. So the purity of this state is extremely large. Let us see another experiment that I can do. So then I want to have that the statistics of my source should follow this characteristic. No longer a Poissonian statistics, but I want to have that the probability to have a single photon in the state that I measurement should be very large. So the probability to have a vacuum state should be negligible. And let me see how can I get this fact by using the heralding properties. So let me consider a source of photons, a pair of photons that are entangled. Just to get you familiar with the name, so in our way to get the photons, I call one idler and the other signal. But those photons are two entangled photon states. And now I'm getting those two photons, those two entangled photon states, and I'm measuring one photon in the pair. So the result of the measurement, since the source is a probabilistic source, the result of the measurement is that sometimes I have one photon and sometimes I do not have any photon. So this is what I do measure when I'm doing the measurements on one of the two photons of the pair. Exactly the same as in a classical light source. So the probability of having 0 photons in the state is large, then the probability of having one photon in the state is going down, so it's a Poissonian statistics. Let us see what happens if now I repeat the experiment, but by doing an heralding, by applying the heralding approach. So in this case, what happens? In this case, it happens that now I'm measuring the other photon in the pair. So I'm measuring the heralder photon that is heralding to the Ungo-Mandel experiment the Ungo-Mandel experiment that I'm performing the presence of the other photon. So from my point of view of the photon statistics, it means that now I'm measuring the signal and the properties of the photon state of the signal only when the other photon in the pair is present. So that means that in my measurement, I'm removing all the vacuum states, all the states where I do not have any photons. So that means that now the average probability to measure a photon in the state is equal to 1, because I'm heralding the presence of that photon. And so that means that in the statistic, I am removing all those states that have no photons. And so what I do end up with the statistics that is very similar to the desired single photon statistics in my wish list. Is it clear? So this is an actual experiment that we have performed in the lab of our single photon heralded source. You see that, so this is a 3-photon coincidence, meaning that we are measuring the clicking of the 3 detectors at the same time, meaning that we are measuring the click of the heralding as well as the click of the heralded photons. So we measure a given count. You see here also the number, 50 click per second. So this is the kind of time that you take in order to do a measurement. You only have 50 times that the 3 spots do click at the same time. So quantum measurements with this implementation are very time consuming. So they do take times. And so we get 50 photons, 50 counts if the delay between the 2 spots are in the order of few hundred nanoseconds, and then the number of counts is dramatically going to 0 when the delay is equal to 0. Okay, so that means that the expected behavior of having an anti-bunched photon state is indeed observed. Okay, so one characteristic that describes the properties of this source is the heralding efficiency, meaning what is the efficiency of having an heralded photon with respect to the efficiency of having the probability of having a pair of photons. Okay, so that efficiency is essentially limited by the resolutions, by the sensitivity of the detector. Okay, so if P herald is equal to P coupled, so the heralding efficiency is equal to 1. But if we lose some photons, so then the heralding efficiency is going down. And therefore, so this is also an evidence, an aspect by which we need to have very high quality photodetector because we do not want to lose any photon. So what is the state of the art? So this is the state of the art of the single photon sources. Okay, we have quantum dot atom alike that have been initially demonstrated in 10 years ago. Then we have heralded photon sources that have been as well demonstrated few years ago. And as you will see, so you recognize that one kind of device that is used in order to make these integrated devices by using the heralding concept is the microring resonator. What are the properties? So the properties in terms of numbers, so the quantum dot sources have the possibility to generate some 25 millions of photons per second, so very high brightness. So the indistinguishability is low. The scalability is low, meaning that you need to have a quite complicated experimental settings. And the wavelength, so where you can generate your photon is quite limited because you need to have that specific electronic transition. And then in the case of integrated devices, so we have a very large different wavelength region where we can generate a single photon. They are very scalable, so we can integrate in many of those sources. I will show you a few examples, maybe tomorrow, not today. And then the indistinguishability is extremely high. I will show an experiment where the two photons are really indistinguishable. The problem is that the heralded concept is based on integrated device by which the single photon generation rate is limited in the order of few hundred kilohertz, meaning few hundred thousand photons per second. So I'm saying that here you have few problems, but despite those few problems, there are companies that are selling those single photon sources. So this is an European company that is called Candela. Here you find the web link of the company. So you can buy, so those single photon source can cost you around a few thousand of euro. And then people are using those sources. So this is Xanadu. I have already said about Xanadu. Here you see the name of the company. I already said Xanadu that is introducing, so they are claiming to have the first modular, scalable, and networked quantum computer. So this is the argument that I was making before during the coffee break. So they are selling modular quantum computers. So the single quantum computer has a limited number of qubits, but if you join more of those quantum computers, you increase the power possibility capacity of your system. And so their source of single photons is based on the Candela device. So let me now try to start to introduce how we can do these heralded single photon sources. And the reason why I'm discussing all the heralded single photon sources is because those are the ones that we are using. Okay, so the basic building block is a waveguide. We already know that in silicon photonics, so the waveguides are some 0.2 micron thick, and the width can be changed, maybe between 0.5 to 2 micron. Depending on the width of the waveguide, so we can have a monomode waveguide or a multimodal waveguide, meaning that inside the waveguide not only the fundamental mode propagate, but also the high order modes. Those modes are characterized by an effective refractive index. So the effective refractive index is nothing else than the refractive index that links the wave vector of the light in vacuum with the wave vector of the light that is propagating inside the modal waveguide. And here what we have is that the effective index of the different modes as a function of the wavelength of the light. So I want to note, to make you to note the fact that if I do consider different modes, I have that the effective index is the similar one for different wavelengths of light. Okay? So this is something that we will exploit later. Then what we do is that we take our device, we inject some light into the device, and then we see how the light propagates, and we try to do the generation of these single photon states. By the way, this is indeed one of these sources that we have developed. The phenomena that we are exploiting is nonlinear optics. I have already briefly introduced you about nonlinear optics yesterday, and the effect is associated to the fact that the polarization vector scale not only linearly with the electric field, but with the square or the cube. And those factors are called the first order, the second order, the third order, and the K1, K2, K3 are the susceptibility of first order, second order, third order. Nonlinear optics tell us that in order to have a Chi2 terms, one needs to have non-centrosymmetric materials, like lithium niobate light. So there are many of those non-centrosymmetric materials. However, silicon is a centrosymmetric material. Therefore, silicon is a semiconductor where Chi2 effects cannot be used. We can only use Chi3 effects. And therefore, so this is what we are using. So we are using a silicon waveguide that show Chi3 effects, but since silicon is not centrosymmetric, we cannot use Chi2 effect unless we break the centrosymmetry. So we have done a few work in that direction, but it's not time to talk. And so here we have second or third order nonlinearities. And the kind of nonlinearities that emerge if you use a second order effect, so those are called second harmonic generation, by which we have that two photons annihilate by generating a photon that has a frequency that is 2 times the one of the two annihilated photons. Or you may have what is called differential frequency generation. And this is a very important process because it's a process that is used in order to make a single photon sources. So in this process, you have that one photon of high energy annihilates by giving two photons whose energy, the sum of those two photons, is equal to the one of which annihilate. And so what we do is that we call this photon the pump photon, and this other photon we call the signal and the idler photon. And therefore, in this differential frequency generation process, we have that one pump photon generates two photons. And what is important is that those two photons are entangled photons, because they are generated at the same time, as well as they have a very fixed energy relationship. And the energy relationship is given by the fact that the sum of the energy of the signal plus the sum of the energy of the idler should be equal to the energy of the pump photon. And those are the processes that happens in second order nonlinear material. But silicon is a third order nonlinear material. And therefore, with silicon, we do have to deal with 4 photons. For example, the equivalent of the second harmonic generation process is called a third harmonic generation process. Here, what you have is the fact that you have the 3 pump photons sum up in order to give you a photon that is characterized by an energy that is 3 times larger than the pump photon energy. Or we have another process that is the process that we are using in order to generate entangled photon sources, by which you have the 2 pump photons sum up in order to generate 2 signal and idler photon whose energy is linked by the properties that the sum of the signal and idler photon energy should be equal to the sum of the 2 energies of the pump photons. And so this means that we have an entangled photon pairs that is generated, that is correlated in time, because the 2 photons are generated at the very same instant, as well as in energy, because the sum of the energy of the 2 generated photons should be equal to the sum of the energy of the pump photons. Is it clear? Huh? This factor? So the third order nonlinearity? So the third order nonlinearity is associated to the fact that, so we are going here to express the polarization as a function of the field, the square of the field, and the cube of the field. Okay? And so if we are here in the cube of the field, you see that we have one oscillation that is determined by the interaction of 3 fields, 3 oscillations. And therefore, in third order nonlinearity, we are dealing with 1, 2, 3, and 4 photons. So we have 4 photons that do interact. And this is the reason why the process is called 4-wave mixing. Okay? We have 1 photon, 2 photons, 3 photons, and 4 photons. They do interact. How do they interact? So that there are many different possibilities that those 4 photons interact. One is by which we have 3 photons with the same energy, omega 1, omega 1, omega 1, that sum up in order to generate a fourth photon that is characterized by an energy that is equal to the sum of omega 1, omega 1, omega 1. Okay? And this process is called third harmonic generation. Harmonic means that is high-order harmonics. Okay? So if those are characterized by a wavelength, let's say, of 1 micron, we have that this photon has a wavelength of 3 micron. No, wrong. So this is 1 micron, and this photon has an energy of 0.3 micron. Okay? So those photons are in the infrared, and this photon is in the blue. Okay? This is, by the way, if you want to generate attosecond pulses, you use high-order harmonic generation. But this is another story. Okay, so this is 3 photons interacts in order to give you back 1 photon. Okay? Another process that may happen when I have 4 photons that interact is so-called 4-wave mixing. Okay? 2 photons, 2 pump photons spontaneously adds up in order to generate 2 other photons was energy is equal to the sum of the energy is equal to the sum of the energy omega 1 plus omega 2. Okay? So in this process, I have the 2 photons that I call 2 pump photons annihilated in order to generate 2 photons that are the signal and the idler photon. Okay? And therefore, what happens in my sample is the fact that I'm going in with a pump photon. I'm going in with 2 photons that are the photons of the pump, and by the interaction with the material, I do get as the output 2 other photons that are the idler and signal photons. Okay? And those 2 photons are, since I am in a single photon level, those 2 photons are entangled. Entangled means time. Why in time? Because they do appear at the same time. Okay? And therefore they are entangled in time as well as in frequency. Frequency means in energy. Why in energy? Because the relationship omega s plus omega I, signal and idler, should be equal to the sum of omega pump 1 plus omega pump 2. And so there is a very stringent requirement on the energy of the 2 generated photons. They are correlated. If I do change omega s, also omega I should change in order to fulfill this condition. It's more clear? I cannot do a nonlinear optical course in half an hour. Other question? So if I'm dealing with conservation law, because this is nothing else than a conservation law associated to the energy, what is missing here as a conservation law? Physics 1. What are the 2 important conservation laws in physics? Energy and pass? Momentum, yes. What was you saying? The mass. Okay. No, not the mass. Yeah. No, because Einstein tells that the mass is not conserved. It's the charge that is conserved, so another story. Okay, the momentum. The other one, in any scattering phenomena, you have to conserve the momentum. And therefore, the momentum is quite important in order to determine which specific energy will be generated. And so this conservation of the momentum is called the phase matching. Okay? And so what you see here is, as a function of the distance between inside the material, so as a function of how much the pump photons are propagating through my material, how the intensity of the generated photon increase with the length. So the longer is the length, the larger is the generated photon intensity, depending on the value of this parameter here. Delta K is the critical parameter there that measures the mismatch between the wave vectors of the involved photons. Meaning what? Meaning that in addition to these conservation properties based on the energy conservation, I need to have also a conservation properties associated with the momentum of the photons. So omega S plus omega E should be equal to omega pump 1 plus omega pump 2. First conservation on the energy. And then I need to have also a conservation load that is associated to the momentum. So the momentum of the signal photon plus the momentum of the idle photon should be equal to the momentum of the pump photon plus the momentum of the second pump photon. So this equation should be fulfilled. And so what I'm doing, so this is written for second harmonic generation, what I'm doing is that the difference, the phase matching between the momentum of the generated photon minus the momentum of the pump should be equal to 0. So that means that in this equation here, what I need to fulfill is the fact that the sum of the momentum of the signal and the idler minus the sum of the momentum of the two pump photons should be equal to 0. So this is called the phase mismatching condition. Why I do need this to fulfill this mismatching condition? Because what I do need is the fact that all the generated photons that are traveling within my sample should have a phase relationship that is equal to 0 in order to add constructively. And indeed, if I do satisfy this condition by which delta K, the difference between the momentum of the pump and the generated photon is equal to 0, so then what I have is that each single generation event adds up, and so the efficiency, so the intensity of the light that is generated because of the constructive interference condition that is fulfilled because all the momenta are satisfying the phase matching condition, so delta phase is equal to 0, so they do add constructively, and so the efficiency increase as a function of the propagation length. If I do not satisfy this condition, what happens is that I do not have any generation because of the destructive interference here. And therefore, you see how critical it is to fulfill this condition. So if the condition is satisfied, so then the intensity is increasing. If the condition is not satisfied, so then the intensity is going to 0. And so what I'm trying to get is to get a perfect phase matching condition in order to satisfy the increase in the intensity. And so this perfect phase matching is described by this formula here, by which the intensity of the generated photon scale with the length of the material at the square multiplied by the sinc function of the phase matching condition divided by 2. Okay? So what does it mean? It means that the longer is the material, the higher is the intensity of the generated photon. Okay? The more different from 0 the phase match condition, delta K, the smaller is the generated photon intensity. And so the optimum situation is the one where I have delta K is equal to 0. I don't know whether you are familiar with the sinc function. The sinc function is the sinus divided by x. Sinus of x divided by x. And it is a function that has a characteristic shape, which is this one. So this is the sinc of x. Let me do the square of the sinc of x as a function of x. And so the function is something that has some oscillation, a maximum, and then some oscillation. So when x is equal to 0, I have the maximum. When x is different from 0, I have a lower value. Okay? And therefore, in my four-wave mixing process, I need to conserve the energy So omega 1 plus omega 2 should be equal to omega pump 1 plus omega pump 2, as well as the momentum K1 plus K2 should be equal to K pump 1 plus K pump 2. And if I do satisfy those two conditions, so then I will have a very high efficiency in the generation of entangled photon pairs. Okay? Question? So I think that is one. So it's time to stop here. What do you think? Yes? Yeah?
Actually, we have one person from the media. There is a local newspaper here, Times of India. It's a very India. She wanted to cover this. I'll announce it here on the.
Okay. So I can speak Hindi if you want.
So we have one reporter here. So we have one reporter here from Times of India. So she'll interact with us for 5-10 minutes so that she has an article on this. So I request all of you, and after that we'll start with the lunch. Okay.
So tomorrow I will continue, okay, this part on the single photon source, because I do want to explain you the undetected photon experiment that I show you at the start of the lecture, okay?
For that we need entanglement.
Exactly.
This is also another topic. First we have to get the
The circuit, yes. But then, I mean, so we can also use entangled photon to do computation. I can show, I will not discuss how we do computation.
Send them for lunch. And
I prefer doing,
so for 5 minutes and then you go.
communication, but for do QKD, for example, so having entangled photon is a resource. So you can use entanglement in order to translate the heat in a second way. But this is going to be tomorrow. Maybe.
Yes, so she would like some of you to give some line or two about your experience of the course, how you are feeling, some feedback. So. She needs it for her. So she is the reporter from Times. So she needs some bites from every one of you. So if you want to.